That's what I'm trying to avoid, damn it. I keep doing that, messing this up. Okay. All right, so our exam will be on Tuesday. All right, let's get to the information from the next. We need 2 more sections before we can do the exam. These are very important sections, all right? This is actually the point in the class where I finally go like, okay, we finally have made it to something where, you know, it's going to get kind of more interesting as time goes on. This is probably the last section of material that you have seen before, quadratic functions. After this, it's usually stuff you haven't seen. So I'm excited to get into the new material. But we got to finish this. So quadratic functions. All right, so whenever we have a quadratic function, our main goal is going to be to graph a quadratic function. By hand, someone gives us a quadratic, we need to be able to graph it. So we're going to talk about what the graphs look like, what their characteristics are, but there are 2 different forms. I'm going to put them up here because they're so important that you understand the difference between the 2. There are 2 different ways, traditionally, that you are going to see a quadratic function. In this form, which I'll give you an example of this in blue underneath. An example of somebody giving you a quadratic function in this form would be something like 3x squared minus 5x minus 2. All right? So you're given f of x, that tells you it's a function. And then over here, you have 3 terms. You've got an x term, right, that's squared, an x term that's to the first power, and then just a constant by itself. All right? This form is called what form? Expanded form. How'd you know that? It says it right there, right? Expanded form. The other option is to have something given to you in this form, ax minus h squared plus k. An example of this would be f of x equals negative 3 times x minus 2 squared plus 12. And this is called standard form. So if I give you on the next test, if I give you a quadratic function in expanded form or in standard form, you're going to be able to need to be able to graph the function and identify all these characteristics that we're going to talk about. But first, identify which one you're working with, because the steps you do to graph this expanded form is slightly different than the steps that you do to graph something in standard form. All right? They're different. By looking at these 2, which of these looks most like what we've been doing? What's that?
As in like what we first learned, or
no, just like the last few days we were talking about like standard form, right? Because this is really your toolbox function, right? Squared. So you know it looks like this. And then the minus 2 is going to take it and right 2, and then the minus 3 out front is going to, let's see, it's going to flip it right over the x-axis, and then the 3 is actually stretching it. And then the 12 out here would take that and move the whole thing up 12. So we kind of already know how to graph that, right? Yeah. But we actually, what we had been doing with this is we were sketching it. We were just getting a real quick, like, draw it real fast, got a basic idea of what it looks like. Today, we want to nail down a better graph, all right, with more detail to it. Almost not, well, we can't get every point on the graph, but we're going to get a few that are very important to us, all right?
Wasn't that part of the homework on the last homework that was assigned? Like 51? Yeah.
To what?
We had to graph a parent function, then graph its transformation.
Yes.
And these 3 points of that transformed graph.
Yes. What 3 points, though? What? It was just 3 points, right?
Yeah.
what we're going to do in here is we're going to say for every quadratic function, here are the things we want to graph. This. So it's going to be, for every graph that we draw, we're looking for the same thing on every one of them. I don't know if that makes sense. Okay, so those are the two forms. All graphs of quadratic functions are called parabolas. The characteristics, they look like a U, right? They either open up or down. That means that your parabola can look like this, like a smile, or it can look like a frown, right? One or the other. And the way you can determine which one it is simply by looking at the coefficient or the number that's in front of the x squared term here. That number in front will tell you if it opens up or down. See how that is an A here? This right here, this is also A. These A's are the same, okay? If that's a positive number, that's a positive number, it opens up. If it's a negative number, it opens down, right? So in this example, we knew this one opened down, right? This one would open up. Got it? So that's what that part 2 says. They either open up or down, up if A is greater than 0, and down if A is less than 0. What if A is 0? Why not?
It's a different thing entirely.
That's right. If A is 0, this is gone. It's no longer a quadratic function, right?
It becomes a linear.
Then it's linear. So so that's why we don't have to worry about A being 0. Okay, they all have what we call a vertex, and that vertex, in this particular case, is the lowest point on the parabola, isn't it? It would actually be our global minimum, wouldn't it? And the vertex on a parabola that opens down would be the highest point on the graph, or what we call the global maximum, right? So for all parabolas, you're either going to have a global minimum or a global maximum. That is dictated by whether or not it opens up or down. That point, it has an x and a y coordinate, right? But it's such a special x and y coordinate that we give it a special letters. We call it the point HK. Instead of XY, HK. Now, if you look at these two formulas, in expanded form, we have A, B, and C. Those are 3 numbers, right? X is our variable. Here, in this standard form, we have A, H, and K. A, H, and K are just numbers. But when something is written in standard form, the H and the K is automatically your vertex. So if I look back at this right here, this example, can you tell me what the vertex of this parabola is just by looking? What is the vertex of this one? So I've heard 212, I heard 212, and I heard negative 212. So what is it? That's right. So when we look at this, and whenever you're trying to find the vertex, you're trying to find the H in a standard form parabola. What you do is you look at the number right here, right? This is negative 2, minus 2. It'll always be the opposite of that. So 2. And then to get K, K is always the number on the outside. And in that case, remember, it wasn't opposite, so this is just going to be 12. Understand? Can you just look at this right here and tell me what the vertex is? No. Which means that what I'm trying to point out to you right now is some subtle differences between these two forms. In expanded form, it's not easy to see the vertex right away. In standard, it is. So you would say maybe this is more advantageous to have this form, right? Maybe. Is there a way to get the vertex of this? Well, we'll see.
We can get the y-intercept.
We can't get the y-intercept, yep. Let's keep going. The next important characteristic on a parabola is what we call the axis of symmetry. And it's not really part of the graph. All right, so it doesn't, you draw the parabola, it's a U. But this axis of symmetry is kind of like this imaginary line that cuts right through the vertex, right through here. And on this one, it would be this one. All right, and we call this the axis of symmetry. And the reason why is because if you take the right side of this parabola and mirror it over, reflect it over that dotted line, it's symmetric, right? A mirror image of itself. So we call that the axis of symmetry. And it has an equation. The equation of a vertical line, it's always going to be x is h. So what's the axis of symmetry for this parabola right here?
It's going to be x equals 2.
X equals 2. So the axis, right? Do you see that x equals h right there? Okay. Axis of symmetry is x equals 2 for this particular one. Can we look at this one and tell what the axis of symmetry is? No, because we need to know what h is. So still, this one looks like the better form, doesn't it? Okay. Let's keep going. Let's keep going. The domain. If you have a parabola, the domain, that should say, oh yeah, a domain of R. All parabolas, whether or not I draw it up or down, the domain would be all real numbers, wouldn't it? Goes in both directions forever. So all parabolas' domain is all real numbers. How about a y-intercept? I'm going to erase this stuff.
Actually, I think that one's wrong.
What's that?
It's supposed to be, the vertex is supposed to be negative 2, right?
Where? Where?
On the standard form, the vertex is supposed to be negative 2.
Opposite of,
Oh, it's opposite.
yeah, it's opposite. Because remember, if we were going to move it around,
Because this way.
yes. Well, I don't know. I don't know if it's because of square. Are you saying this should be a negative 2? Remember that we had a parabola, right? That's what squared meant?
Right.
But then which way did we move it? If we see minus 2, which way did we move it? Right 2, right? And then we flipped it over, and then we moved it up. So where is that point? We moved to the right 2 and up 12, didn't we?
Right.
That's this. You see?
I think what you're trying to do is put in the negative 3 alongside that negative 0 to find the positive 2. But that doesn't really have much to do with it. All that has to do with the actual slope, per se, of the parabola itself.
You mean the negative 3 out front?
Yeah.
Yeah, that controls the shape vertically, like a stretching or compressing of it. And then, of course, a flipping. Okay, so let's look at this. If I have a parabola, I can pretty much draw it wherever I want, right? Am I going to hit the y-axis?
Eventually.
Eventually? Guaranteed?
Guaranteed.
No matter how I draw it? So if I try and draw one that opens down, eventually, right? Eventually I'm going to have to cross through the y-axis somewhere? Eventually. So all parabolas, no matter what, have a y-intercept. And how do we find y-intercepts of functions? What's the unique characteristic of that point? What do you know for sure there? X is 0, right?
Y is whatever.
And y is whatever. So in order to find the y-intercept, what do we have to do to find a y-intercept? Set x equal to 0, right?
As of x is 0.
That's right. No. Set x equal to 0.
X equals.
You want to know what happens if you plug 0 in for x, what comes out, right?
Right, that's what I meant.
So we're guaranteed at least one, just one?
At least one.
At least? What do y'all think?
Wait, no, it's just one.
It has to be just one, right? For a parabola, it opens up or down. It must be 1. It couldn't be 2, because if it was 2, if it hit in 2 places, you would now fail the vertical line test. You would no longer be a function. So there's always just one y-intercept. So that's why I put there a y-intercept. And then for x-intercepts, what do y'all think? I can have 1, 2, or what? Or none?
Depending on where you put the parabola.
Yeah, that depends on where the vertex is, right? So let's say I have a parabola that has a vertex here. Can you draw me a parabola that would hit the x-axis twice?
Yes.
Just make it go down, right? That's pretty simple. Okay, what if I have another parabola that has a vertex here? Can you make it hit, well, can you make it not hit at all?
Make it positive.
Make it open up, right? Then you wouldn't have any x-intercepts. And how would you do it so that you only have one x-intercept?
It said it's
Set it
0.
on the x-axis itself.
Set what on the x-axis?
The vertex.
Put the vertex on the x-axis, and open it either way, up or down, right? So in this case, we have two x-intercepts, right? This case, we had no x-intercepts, and here we have one. Agreed? Is there any other possibility? Can we get 4 x-intercepts? Can we get... No. No matter how you draw it, these are the only 3 possibilities. Do you all agree with that? Okay. So we know that when it comes to x-intercepts, you may have 2, 1, or none. All right. I won't really get into this. This is where you could go and just move things around and blah, 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 blah. But it has the axis of symmetry. You all see that dotted line down the middle? Okay. All right. So we're going to practice real quick converting from one form to the other. We want to be able to go back and forth. If someone gives you a parabola in standard form, can you switch it to expanded, and vice versa? So let's say we have f of x is -2 times the quantity x plus 3 squared plus 8. Before I do this, we haven't talked about why we would even want to study parabolas. Right? Parabolas are one of the more interesting things to study, and so let's talk about some things that might interest you with parabolas. So, you want to be my volunteer today, sir? No? Okay. Okay, you can be my volunteer. You just stay right there, okay? All right, so I'm going to throw a marker to you.
All right.
All right? Everybody watch the marker, right? So here we go. Right, throw it back. Heads up, everyone. Okay, so if you throw something through the air, right, it's going to travel in some curve-looking thing. Well, that curve is a parabola, guaranteed. If you're standing on any planet with any gravitational field, any sort of gravity on it, then you're going to have some sort of parabola form. All right? So why would it be important for us to study something like that? Well, you can go. Are you answering that? You have an answer? Go ahead.
Yeah. Well, ballistics is one.
Okay.
I know they use it a lot in, of course, ammunition and, how it affects, this, that, the other.
Mm-hmm.
Rocket science, what?
Gravity plus the Coriolis effect when it comes to sniping, right?
Well, not just that, but anything in general. Trajectory,
Mhm.
trying to figure out, okay, well, if I have this piece of, marker when I throw it, X fast, how, where is it going to hit on this?
There you go.
planet?
Exactly. That's exactly what I'm getting at. Okay. You have back in the old days, right? I'm going way back here. Okay. This is going to be my rendition of a castle. Okay. There's a castle. You like it? There's a castle. And they built castles to keep people out, right? And so they would start to try and storm the castle, and they start, throwing stuff at it. And then they got these catapults, right? And they start launching stuff. And the whole idea is to maim and kill and scare the people inside, right? To the point where they want to give up. Well, if you're just lobbing stuff randomly at this thing, sometimes you hit, sometimes you don't. Every one of those are parabolas, right? If you study this path a little more in depth and really get an understanding of how parabolas work, then you could actually determine, if you wanted to hit here, you could determine the parabola that would do that, right? That would just correspond to some x-intercept of some parabola, right? So we got real good at this. So I know I've had in classes before, I've had students who were like in artillery, in the military, and they would use these tables or like a computer, and they would put in, how far the target is and all these different variables, and it would know the correct parabola to model that situation. They could hit their target within a couple of feet, right? Miles away.
Sometimes even closer.
Yeah, so that need to man's need to like kill each other is a huge motivation when it comes to technology, isn't it?
It's true.
Advancing, right? Our need to hurt each other and not get along, that motivates us, right? We like that stuff. Yeah, this mine, no, get away, okay, you know. So, all right, that's one, you know, artillery. Now, something a little more passive, all right? How about communication? Here's the Earth.
Wouldn't a communication satellite be more along the lines of, say, like an absolute value for using a satellite? No.
There we go. Two people on opposite sides of the world that want to communicate with each other, right? You have oceans between each other, so what do we use? Satellites, right? So how does a satellite work?
Well, cell phone builds it to the signal.
So yeah, we'll use a cell phone as an example. So your cell phone, right? You're sitting here, you make a call, it sends a signal out, right? Does it know where the tower is? Does it know where?
It's supposed to go to the nearest tower.
But does it know where that is?
No.
It sends a signal out in every direction. So you have a signal that comes out of this in every direction. So imagine just like glowing, all this electromagnetic radiation coming off your phone, right? And some of it goes and hits a tower that's out here somewhere, right? And that tower has receiving antennas on them.
Leads up to the satellite.
Hold on. That antenna, how does that antenna capture that signal? It uses a parabola. Somewhere in there, you're going to have a parabolic shape. So what the unique property of a parabola, here's a parabola that opens down, right? What I'm going to do is let's look at it sideways instead. The unique property of a parabola is this. If there's some electromagnetic radiation coming into this parabola, so imagine it's, you know, your signal from your cell phone. If that signal's coming from here and it hits that parabola, it will bounce off that, it will reflect down to this point. And there's a little receiver that comes out, piece of metal, with this ball on the end, and it's sitting there, and this is the thing that's actually listening for the signal, right? But the unique thing about a parabola is this. It'll bounce to that point. It doesn't matter what direction that signal comes from. It will reflect perfectly back to that point, no matter which way you come in. They all go to that. All right, to that point. We actually call that point a focus. And a parabola is the only shape that does that. If you just take a circle, right? We know what a circle is? If you just take a circle and cut it in half and put it next to the parabola as a half circle and try and do the same thing, it's not going to work. Your reflections will come in and reflect, and maybe one of them will hit that, but another one is going to miss it. This curve is not perfect to focus everything at one point. Only the parabola will do that, which is why your dishes, those satellite dishes out there listening, have to be parabolic. All of them have to be parabolic. And that's the same way these telescopes work. You know, they're looking out to distant galaxies, right? What are they doing? They're looking at light that we can't see with our eyes. So what they're doing is they have this huge parabolic mirror, right? These observatories up on tops of mountains. They've got this huge parabolic mirror, and they're looking into space, into complete, what we would see complete darkness. And this parabolic mirror is taking all that, what we see as darkness, and light that we can't even see with our own eyes, and it's focusing it all onto one place. And it amplifies everything. Yes?
So it's a funny story about that.
What?
The Hubble telescope, when they first put it up there, they got their math wrong. And so they created this big, gigantic satellite telescope to look out with. They created it with the wrong parabola.
Yep.
And it became nearsighted.
That's right.
And so they had to go fix it.
That's right. Yep. Well, it's very hard to make a perfect parabola. I mean, it's very difficult to manufacture one correctly. And we're talking about a big mirror. It's hard to make it perfect. And they really couldn't test it until it was up there. So, okay, so the parabola was somewhat useful. Here's another application which I don't know if you've ever seen this before. If you've ever owned a flashlight that has, you know, turn on the flashlight, you got this beam of light, right? and sometimes you can turn the front of the flashlight and the beam of light like will spread out, or it'll go in like this. All that is a light bulb. So the light bulb's sending out light. We're looking at the side of the flashlight. Here's the flashlight handle going back. Whoa, what happened? Okay, this is the handle of the flashlight. And inside there is a bulb. And on the back side of it is a parabolic mirror. So what's happening is that the light that comes off of here hits and goes straight out. The way they have this mirror set is that it hits and goes straight out. Hits, goes straight out. Hits back here, goes straight out. And then what happens is you turn it and it moves that parabola backwards or forwards, depending, and it screws up all this stuff. Like it screws up the perfect coming out like that, and what it does is it spreads it. And so instead of coming out like that, it'll come out like this and be a little bit off. And the next one will be just a little bit off, like that. And so what you get is the spread out effect. And you'll notice that when you spread your light out, it's not as bright, right? It's because you've spread all those light rays out over a bigger area. But that back mirror has to be parabolic. Your headlights work the same way. You ever go look at your headlights on your car, you'll see a mirror in the back. That has to be parabolic for it to work properly. Okay. So parabolas, that's all I'm trying to get you to see, is that parabolas are there every single day of our life, but they're used.
That's true. The
Is the
Death Star was a parabola.
The Death Star is a parabola?
On the Death Star, there's like a big satellite.
Oh, yeah. That's a satellite?
Yeah.
Oh, yeah. Built into it?
Yeah.
Oh, okay. Cool. I don't know. I'm not a Star Wars person, but I know what you're talking about.
Focuser, kind of like how a curved mirror works.
Yeah.
A guy made that. He put it on YouTube. He got a like satellite dish and put like 10 years in there. Focused it on the sun.
Yeah.
Flashed the sun and he was like lighting stuff on fire with it.
Oh, yeah. You can.
Get one of those.
There's a Mythbusters episode where they have this thing called the something death ray.
Yeah.
Or Archimedes death ray, right? So, okay, let's get back to this. We want to be able to graph parabolas. All right, so let's convert this to standard form. So we want to go from here to this. Ax squared plus bx plus c. That's what we want to do. Well, this is going to be pretty clean. All we need to do is remove this parentheses. But to remove the parentheses, you have to square it. So just be careful with that -2, because that -2 is going to come through here in a second. And that -2 will have to pass through whatever this becomes, right? So tell me what that becomes when you square that.
X squared plus 3x plus 9.
Plus 3x plus 3x, 6x plus 9, right? So that's what you would get if you squared that. And now pass your -2 through.
So it'd be -2x squared minus 12x minus 18.
Minus 18 plus 8,
Which makes it minus 10.
which makes it -10. So -2x squared minus 12x minus 10. That is now the same parabola we had here, expanded out into expanded form. Recognize, if you will, please, the A here is still the A here, right? That never changed. But H and K, right? What was H for this one? What was H? -3. Remember, H is always the opposite of what you see here. H is -3, and K was 8. Right? We've lost that completely this way, right? We've lost the vertex. That's what we're going to do next. Okay? So how do you go backwards? So let's take the same problem now, and I'm going to go backwards with it. So we know what the answer should be, right? The answer should be that, what we started with. But let's act like we don't know that. So unfortunately for you, or fortunately, depending on how you feel, to do this, you have to use completing the square to do it. So we talked about that at the end of class last time. What was the first condition you needed in order to complete the square? You need to have a 1 on the x squared, which we don't. So the first thing I'm going to do is factor -2 out. So I'm going to take -2 out of all terms. Is that right? That doesn't seem right. Is that right? Yeah. What I'm missing is the x. That's what I was missing. It's like, that does not look right. Pardon me? Yeah, so now that we've done this, what we do is we look at just in here, and we try and figure out that hidden 0 in there, right? That hidden 0 is going to come from which number? What are we going to use?
6.
The 6. It's the number in front of the x. And we have to make sure we keep the sign, too. If it's positive, we want to be using positive. So I'm going to take positive 6 and do what with it? Divide by 2. Always 2? Yes. Okay, what is that equal to? 3. And then what we do is we take that number and we square it, and that gives us 9. And that's the number that we're going to use for the hidden 0, isn't it? Yeah? So I'm going to see a hidden 0. I'm going to realize it. Where am I going to place the hidden 0? After 6x. So I'm going to rewrite -2 x squared plus 6x. And then what? Plus 9 minus 9 plus 5. Close my parentheses. First 3 terms, guaranteed, will factor to a perfect square. Right? That's a perfect square trinomial, a guaranteed factor, so be real careful with the way you write your parentheses here. You have -2 times, but this is going to turn into another parentheses squared, isn't it? So what goes in this parentheses? X plus 3, and that's where we take that number, right? And then that quantity squared. And then what number is left on the outside now? Or -4. What's the last step? Distribute the -2 through to both of those. Here and here. And when you do that, you will get, I'll do it right here, -2 in front of x plus 3 squared. And then what? Plus 8. That's what we wanted, right? Okay, that's how it's done. Y'all okay with that?
Just a quick question.
Yes.
Now that's always going to be divisible by 2, then?
No. It will not always be divisible by 2. That's a very good question. Let me see if I have another one. Well, you know what? I'm going to show you something else. So the completing the square, we'll do one that's not divisible by 2. The completing the square, would you agree, works? Yes? Yes? But there's actually a shortcut to completing the square that I can show you. They don't like us to use just the shortcut. In a class like this, they want everyone to be comfortable with this. But when it comes down to it, the shortcut will get you there, and you won't have to suffer through this. So let me show you the shortcut. You ready for the shortcut?
Let's get shortcutting.
Are we going to do the same problem?
Yep, and do the exact same problem with the shortcut. The shortcut is what's called using, or what we're going to use for the shortcut is we're going to use the Vertex Formula. It's called the Vertex Formula. And this is a gift that's been packaged up and given to you from Calculus 1. In Calculus 1, you can show where this formula comes from, all right? It's actually a very simple result that we get in Cal 1. In this class, we can't see why it would work, but that's okay. Do you agree I'm trying to get it to, I'm trying to turn that into this? Right? That's what I'm trying to turn it into? So there's 3 things you need in order to have it in this form. You need to know what A is. Do you know what A is?
Yes.
Yes. -2, right? Do you know H? No. Do you know K? No. So if I knew what H and K were, wouldn't I be in business?
Yes.
That's what the vertex formula is. It's a formula that tells you what H and K have to be without you even having to worry about it. All right? So don't ask where it came from right now, because I'll just tell you calculus. H will always be negative b divided by 2a. Always. Negative b over 2a. Now remember, this is written in the form ax squared plus bx plus c, right? That's the form we have up there. So when I say negative b over 2a, I'm saying negative b over twice that number. That's what h is. K is equal to f of h. What this means is plug h into the function. And the answer will be your k value.
When you say plug into the function, you mean just plug into this expanded
Yep.
function?
Yep. We're going to do this problem now, but this is the actual formula. All right, so here we go. Let's get h for this particular problem. For this particular problem, h will be negative b, which means the opposite of b, doesn't it? What is b for us? Negative 12. And we want to take negative negative 12, which means 12. So we have positive 12 over 2 times a. What's a for us in this problem? Negative 2. So you get 12 over negative 4, which is negative 3, right? Negative 3. You with me? Okay. Now, to get k, all we need to do is take that answer and plug it into the function. Take this answer and plug it back in up there. So this is negative 2 times negative 3 squared minus 12 times negative 3 minus 10. Whatever that is. It's going to be 8, but go ahead and do it yourself. It's negative 18 plus 36 minus 10, which is 8. You agree? So now that we have what h and k are, I can write it out. Here's what my vertex is. My vertex is negative 3, 8, right? It's my vertex. So let's write the standard form. It's a x minus h squared plus k. So we said a was what? Negative 2. Now be very careful with this part. This part, again, this is the thing that always trips people up. X minus h means x minus negative 3. So it's really x plus 3 squared, and then plus k, but k is 8. Same thing we got, right? No completing of the square there at all. How do you feel? It's all right?
I like that.
So, yes,
Yeah, can you explain where you said where we would get confused?
you would get. Okay, so look at this formula right here, right? X minus h. A lot of people will just want to put x minus 3 here and not realize that the formula is saying x minus, right? What's h right there? That's negative 3, but you have to subtract it. So it's going to switch it to a positive. Just be careful with that. Like, what if this had been positive 3?
It would have been
X minus 3, right? Okay, so just be careful.
negative.
All right, so we're going to have a set of steps now, a procedure that I want you to follow on the test, which is on Tuesday. This is the procedure I would like for you to follow when it comes to graphing quadratic functions. I don't want you to just type in the parabola into your calculator and draw me what your calculator draws. All right, this is what I want to see. So the first thing that we want to do when we graph a quadratic function is, I'm going to list these out. Well, you know what? We'll refer back to them. We'll just look back here. First thing we want to do, make sure you're looking at a quadratic function. Now that might be something that's obvious to you, but we're going to study and graph. We have a list of 6 different things we're going to graph in this class. Lines, which we've done, parabolas, which we're doing, polynomials, which comes next, rational functions after that, exponential functions, and logarithmic functions. Those are the 6. Every one of them is different on how you graph them. So when you're looking at the function to graph it, make sure you're looking at a quadratic function. Next thing, yes?
The vertex formula, will you
Yes.
have it, like, on the, like, in the icon?
The vertex formula, probably not, because it's just negative b over 2a. Right? H is negative b over 2a. You just need to know how to use that.
So we're also going to be.
You can get a tattoo. If you get a permanent tattoo, you can write any formula you want. You can have anything on you. It's got to be permanent, though. None of that stuff that lasts for a week or whatever.
So I'll just write all, it's get a text with all the math formulas.
Whatever you want, man. I'm not going to hold you back. Go for it.
On the test, it's like a kind of a long formula, are we gonna have it on the test, like show us? Or the
What formulas do y'all think y'all need?
like the difference quotient, I guess?
You know what? Let's look at the test from last time. We'll look at it and I'll see what I had on there, and then we'll determine from that. Okay? All right, so we're going to make sure we're looking at a quadratic function. We're going to see if it opens up or down. That's the next thing. Does it open up or down? To do that, all you're looking at is what? The A, right? The A? Okay, find the vertex. Okay, that's the next thing we're going to do, find the vertex. Then what we're going to do is what's called a quick sketch. The book doesn't do this way. I doubt any of the tutors will, and it's not because I'm trying to rebel or anything like that. It's just that this, to me, makes the most sense. Thank you. As soon as we have whether or not it opens up or down and the vertex, I want to just draw a quick picture. Right? And then, once you draw the picture, you ask yourself, do you have any x-intercepts? Right? If you do, then you go find them. If you don't, you just move on to the next step.
I see why you said that.
You
That
see?
makes sense.
Okay.
Because if it's, up here, then it goes positive, why are you gonna waste time?
That's exactly, you're saying exactly what I mean. If you know this much, that the vertex is here and the parabola opens up, why go waste your time trying to find x-intercepts when they don't exist, right? And that doesn't take that much time to do. Okay, then we have to, after we get our x-intercepts, if we have them, we will get the y-intercept, which we said we're guaranteed exists, right? And then we will plot all the information and we will sketch the parabola. So I have our first example. And the first one's pretty easy. Yeah, this first one's really easy. So let's see how this goes. When I say easy, like we're not going to run into any issues when it comes to any of the steps here. All right. First thing. Everyone have it written down? Because I'm going to go back to the steps. Step A. Do we have a quadratic function? Yes. Okay. B. Does this open up or down?
Up.
Up. It opens up because A is what?
Positive.
Positive. It's 1, isn't it? Greater than 0. So A is 1. It opens up. C. What's the vertex? So how are you going to get the vertex? How would you like to get the vertex? Do you want to complete the square or do you want to use the vertex formula?
I just say,
Vertex formula? Okay. So if you're going to use the vertex formula, you need the formula h equals negative b over 2a, which for us is negative 2, positive 2. What is it? Positive 2 on top. Because look, it's negative b. That's the opposite of what you see. Be careful. Negative b over 2 times a. So 2 times 1. So this is just 1, isn't it?
Yeah.
Okay, what do I do with that? Plug that into the original function. So k is going to be f of 1. So can you plug 1 into this, please? Tell me what you get. You get 2. Should be 1 minus 2 plus 3, which is 2. So you have a vertex, it's the point 1, 2, isn't it? Is that okay? What's the next step? Quick sketch. Okay, real quick sketch. Part D. My vertex is out 1, up 2. So here it is, right?
And it's positive,
Right?
so you're not gonna have.
And it's positive, it opens up, which means no x-intercepts. So I'm not going to go look for them, right? No x-intercepts. So I move on. If I move on, the next thing is to find a y-intercept, right? How do you find a y-intercept? Careful. Plug in 0. Plug in 0 to the function. So plug 0 in to this, and what do you get? 3. Got it? And now the last part, part F, is to draw me the picture. Well, we don't have a lot of information, do we? We don't, but we have enough, okay? We have enough to draw a pretty decent picture. I know that I have a vertex at 1, 2, right? So I'm going to put this point here. I'm going to label it 1, 2. I know that it opens up, right? The only other piece of information I have is this, which is a y-intercept of 3. So if I come up here to 3 and draw a dot, I know my parabola has to go through that, right? So if this is the lowest point on the graph, right, and it has to go up to there, then it's going to curve up like this, right? Not straight, not like a V. It's going to be curved up to this. So it's going to look like this and go like that. And now the other side is going to do the same, but what I could do to try and be pretty precise with this,
You can put the line
I
there.
could draw that axis of symmetry in.
And that way, it would lie at 2, 3.
Yeah, you can actually figure out where that is, right? If you go up, right, this is 1 over, isn't it?
Yeah, so you can
So if I just go 1 over on the other side like that, this is actually the point 2, 3. 2, 3, isn't it?
Yeah.
'Cause if this is 1, then moving 1 over is 2, so it's 2, 3. Oh, I got you. And then I can go like this and draw it. And that's a little more precise than this one. Right? I have a little bit more information. And that's what I'm looking for.
On your test, do
Uh-huh.
you want those points labeled, like specifically?
I need to be able to see that you know what they are. So if you put like 1 and 2 here like this, I can kind of tell, right? I can kind of tell that that's the point 1, 2.
But you would prefer it.
But I prefer you to get used to, and I would also, you know, get used to doing things like this, like labeling your axes, X and Y. You know, just more detail, the more detail, the better. What I'll see some students do, not necessarily on parabolas, but as we move on later on, they'll do something like this. Like, honestly, this will be an answer on the test. And you know what that is?
Not really.
That's the picture off their calculator, exactly. And they won't label it or anything. That'll be it. I've seen that before.
Well, you can get it on your calculator. If you have one of those fancy ones, you can have a name. Get it.
Oh yeah, you can label everything.
Does that get you something?
That gets you nothing at all.
And then you're like, what is the line?
I gave my Cal 2 class to their first test today. And I don't know yet, but it's very telling because I hand out the test and about 6 or 7 students went straight to their calculators. like right to their calculators.
That's good or bad?
That's really bad, because you don't need anything on that first test. You don't need a calculator for a single thing. But these calculators are so smart nowadays, they do a lot of the calculus. So they have to show their work. They have to show their work, so even if their calculator is able to help them, they still have to show how to do it by hand.
Well, I guess
So-
I guess that's telling whether or not they're right or wrong.
It's too much of a crutch. It's too much of, they're depending on it too much. All right, let's look at 3. 3 looks like the most interesting one here. Oh, you know what? We didn't answer some questions here. Oops. We got the graph, right?
Yeah.
The domain and range. What would the domain of that be? All real numbers. Range. Remember the picture? I just erased it. Yeah, the range would be from 2 to infinity, right? So we would say like 2 infinity range. Where is f increasing? So it'd be increasing from 1 on and decreasing from negative infinity to 1, yes? Okay. Do we have a maximum? Do we have a maximum at all? No? Minimum? Where does...
Yeah.
Right there. The minimum is the vertex, right?
For what?
What's the maximum or minimum value?
The minimum value on Q1. What's the
The-
vertex?
Okay, so where does it occur? So where does this minimum occur? What we mean by that is where, meaning the x. It occurs at 1. That answers part D. What is the minimum value is the actual value of the function, which would be 2. So at x equals 1,
Oh, okay. So
you have a minimum value of 2.
So you want to say, okay, well, X is this, Y is this.
That's basically what that's asking. D and E is asking you for your x and your y.
Okay.
You look like, where? Okay, tell me where does the minimum happen in terms of the x value? At what x value do you have it lowest?
Vertex?
Yes. Where does it happen? At what x value? Does it happen over here at negative 1? No, my lowest value is not over here, right? Is my lowest value over here at 3? Is my lowest value right here at 1? Okay, that's the question for part D. Find where the maximum minimum occurs. It's occurring at 1. Now, what is that lowest value? That's part E. 2? Make more sense?
Yeah, I got it.
So how would we write, like x equals 2?
Okay, to answer D, you would say
Yeah, 'cause
x is equal to 1, and on E, you would say y is equal to 2.
Okay. Okay, because in the homework, there was questions like that, and I was like,
Yeah.
I just put the vertex again. 'cause I was
Like the whole point?
Yeah. 'cause I was
See,
like,
the whole point kind of incorporates both, right?
Yeah,
But let's make sure we're clear, that we can clearly distinct between where it's happening and what it is. Like, where does it occur and what value is it? Those are two different things. Let me give you an analogy. You have time, right? And here you have h for the height of a projectile we're going to throw through the air. We throw it through the air, it hits the ground somewhere, right? We could ask ourselves, when does it hit the ground? And that would correspond to the x-intercept, wouldn't it? In this case, t, though. If we look at this would be the highest point of the projectile. The two things I would ask you is, first, when did it reach its highest point, which would be this? And then I'd ask, what was the highest value it reached? And that would be this. See the difference between the two
Yeah.
questions? That's what we're asking here.
I've seen the same thing in physics, and I guess it's, even though it's the same thing, same question, it's just a different way to ask.
Yeah.
That's what it's sort of-
Is it clear now, though?
Yeah.
Yes? Okay, good. All right, now let's move on to 3. You want to try that one on your own, or?
Yeah.
Yeah? Okay, go for it. Give you some time. You can do it. Just go through the steps. Everyone write, well, I'll write it down up here, and then I'll put the steps back up there. Looks like Ariel bailed on you, huh? Maybe I upset her with my comment the other day about my niece. Right. He thinks all Ariels are complete losers. I'm gonna step out for a minute because usually students work better when I'm not in the room for some reason, at least to get started. But y'all help each other out too. Progress or no?
Yeah, working on it.
No?
Don't rush perfection.
Who's hung up? Who's hung up? It's all right to be hung up. Yeah, it's gonna be a fraction. Yeah, just leave it as a fraction. But then you have to plug that in. So if you don't feel like plugging that in, you're gonna have to do a decimal and then get your calculator. So, yeah, this is where things start getting a little bit hairy. Yeah, 2 decimal places is fine. I worked through that kind of quick, but anyone get an H yet? 4 points?
Maybe I did.